folks, let's get started. I'm Professor Srinivas from the University of Illinois at Urbana-Champaign. Let me introduce our first speaker, Professor Jawad Lavai from Berkeley. And he's going to talk about cyberattack and anomaly detection for power systems using machine learning techniques. And then we'll have a small Q&A session after that, and then we'll have the next speaker. So Jawad, the floor is yours.
Hello, everyone. It's my pleasure to be here and talk about the research funded by C3AI. And I'd like to thank the organizer for putting this wonderful in-person event together. I'm going to talk about cyberattack anomaly detection for power systems using machine learning techniques. And this is joint work with my colleague, Samay Sujudi at Berkeley. So the outline of my presentation is as follows. First, I'm going to give you a quick overview of what we need for a modernized power grid. And then I'm going to move on to the opportunities for the design of learning techniques using AI and optimization. And after that, I quickly mention two of the problems that we've been working on and funded by this project, which are related to anomaly detection and cyber attack. And I'm going to show you some real simulation on the US grid with about 85,000 nodes. So the US grid, as a civil infrastructure system, is the largest machine on Earth with over 200,000 miles of transmission lines and millions of devices. And a traditional grid, it has a layered architecture with 3 layers. We have got generation layer, transmission layer, and distribution layer. And the way that we operate this system is based on a multi-scale approach. On the scale of weeks to years, we work on problems like expansion, upgrades, and the design of policies and the regulations. On the scale of hours and days, we work on market problems. Then on the scale of seconds and minutes, we work on learning and optimization problems. And that's where I'm going to focus on today. And on the scale of milliseconds and seconds, we're going to work on control problems. And the way that we operate the system is based on some assumptions. At the distribution level, we assume that most of the humans in the system are passive players, and as a result, the system is mildly stochastic. And we've got a lot of gigantic generators that provide inertia and stability for free. And more importantly, when we work on the heart of the power system with the transmission network, we assume that we have very simple models that are fairly accurate, and we have a modest number of controllable devices. But now we are going to go from this legacy grids to modernized grid where it's sustainable, it's reliable, it's resilient. And all these assumptions and properties would go away, and a multi-scale approach is no longer valid because we don't have separation between these problems. And then we have to deal with a lot of challenges. We have a lot of new devices in the system, like power electronic devices, how to model them, how to deal with millions of humans in the loop, how to deal with renewable energy, distributed generation, and also reliability and resiliency. And there are 2 sides to this story. One side is the hardware, that how to design the hardware and the infrastructure. And the other side is how to put all these devices together and make it work, like millions of solar panels, and make sure it works. And that's where computation plays a role. For all these problems, going from the scales of years to milliseconds, computation is the bottleneck. And we have to deal with computational issues, and that's where this, opportunities on the cyber side would show up. So technically, we want to work on data-centric operation, and for that, we start with data. We need to have tools, maybe based on AI and ML, to extract reliable knowledge. Then we go from knowledge to decision, and then we take action. And we've got all kinds of sensors to collect data that has been going on for like half a century. Recently, we have new types of data, new types of sensors, for example, DLR, dynamic line rating, which allows us to model the system in a better way and have a real-time, for example, estimate of capacity of a line. So there are a lot of opportunities based on the new types of sensors that we have that allows us to get new data, informative data. And when we have a data-centric operation, on the positive side, we are able to increase the efficiency of the operation. We can have a better monitoring system. And more importantly, we can increase the capacity of the network, for example, by over 10% without the need to expand the grid, to put physical devices like transmission lines in the system. But the downside is that if the operation is data-driven, it's going to be vulnerable to attacks and faults. And that's what I'm going to talk about today. So let's move on to learning and see what are the opportunities and why we want to design tools. A nice motivating example is Campfire in California that happens in 2018. And I was there. I was at Berkeley when this happened. It was really catastrophic. That killed 85 people, and that destroyed over 18,000 buildings and cost about $16 billion. And the reason why the fire happened was the electricity grid. A power line was down for about 15 minutes, but they couldn't detect this event in time to calculate the best action. So if we had better learning tools, we were able to detect this anomaly, calculate the right actions, and have a localized blackout as opposed to a larger scale fire. So technically, we want to design algorithms that work on data to give us good knowledge, and that's where we can use AI and learning. And this learning in power system has been going on for half a century through a problem that is called power system state estimation, or PSSE. In this problem, the data corresponds to all the measurements that we get. For example, we measure active and reactive powers at nodes. We measure voltage magnitudes at nodes. We measure flows over lines. And the knowledge is really about the state of a system. And that's really about the voltages or complex voltages at different nodes. And we solve this problem every 5 to 15 minutes in practice for two reasons: monitoring and then control. And if you go back in time and look at like a 2003 blackout that happened in Northeast, and that was larger scale, that was catastrophic. But a report came out of that was written to the Prime Minister of Canada and the President of the United States. And repeatedly in that report, they mentioned that the failure of PSSE just triggered this. So PSSE, as a basic learning problem, is a bottleneck. If there's a problem there, that would have some, ripple effects on the grid. And to model, all these learning problems, it's really about, mathematically, it's really about learning over a network. For example, we have a network here, and at each node, there is some quantity of interest, like xi, that is unknown. Putting all those xi's together, I'm going to get some unknown state for the system. And the goal is to find x, the state of a system, from possibly compromised measurements at nodes and over lines. And each measurement has some nonlinear equation. Here I assume that the nonlinearity is quadratic, but could be any polynomial equation. So technically, we've got an equation like this. Bi is the measurement, x is the state, mi is the model used by the operator, wi is the regular sensor noise, nu I is the quantity of interest. It's very important. Nu I could be 0 or non-zero. When it's 0, that means the equation is healthy, the measurement is healthy. When it's non-zero, that means the measurement is compromised. That could account for fault, the error in the model, or a cyber attack. And if you want to learn X from B, there are two challenges. The first challenge is nonlinearity, and that means you have some NP hardness in the language of computer science. And the second challenge is the adversarial nature of the problem, because I don't know what subset of nu I is 0, and there are exponential number of scenarios. And I'm going to focus on the second challenge here. So as far as this problem is concerned, there are two different scenarios that we call them uncoordinated fault or coordinated attack. In uncoordinated fault, technically what happens is the following. Let me just go back. Okay, in uncoordinated fault, at random locations, measurement would be manipulated for whatever reason. And then in coordinated attack, it's not going to be random locations. Someone has engineered that attack on the system. So technically, a small geographical area is manipulated. The data for that one is manipulated with the hope of having some global effect on the network. For the first problem, our goal is twofold. We want to identify the attack location or the fault location, and also recover the state of a system everywhere in the network. And that falls into a classical problem in machine learning like matrix sensing. The second problem is really more related to power, And that's challenging to solve because when a part of the network is attacked, it's really impossible to recover the state everywhere. We lose the notion of observability. Then our goal would be a little different. First, we want to identify the attack region, like the shaded area. And then instead of recovering the state everywhere in the system, we want to recover it just for the uncompromised part of the network. And we have designed estimators to deal with both of these problems. Estimators based on ML and conic optimization. So let me start with the first one, that we call it anomaly detection. In anomaly detection, you can look at two things: how to design the best attack or how to do the best defense. And I'm going to work on the best defense. And that problem is related to a problem in machine learning that is called robust matrix sensing. So technically, we come up with conic optimization. There are some hyperparameters that we need to design. And under some hideous conditions, this estimator is going to work. And that's where mathematics plays a role. And a lot of conditions, but based on assumptions, we can simplify them and make them useful for power systems. And what we've got at the end of the day is that if the number of faults in the system or wrong measurements is on the order of the square root of the number of good measurements, then we can solve the problem. We can identify the locations of an attack. So we did some simulation on one European network. In this network, there are about 5,000 measurements, and up to 150 of them are compromised at different locations. I don't know what location. This estimator was able to solve the problem correctly, and the estimation error was exactly 0. So this estimator really works if we have up to 150 measurements compromised out of 5,000 measurements. So we tested on real data. That was really promising. And this used a lot of notion in machine learning that is just hid under the carpet. But what I want to talk about now, which is more important, is Cyberattack, because that's much harder. To solve a problem related to Cyberattack, imagine the data for this part is compromised, and then that's going to have some global effect. We want to figure it out. There is a notion in machine learning that is called mutual incoherence. We built upon that one to make it useful for power system. We call it graphical mutual incoherence. This is defined for every line of the network is a number between 0 and infinity. And we're going to focus on something that we call them boundary lines. Boundary lines are the lines that connect the compromised part of the region to the rest of the network. So we have a theorem after a number of lemmas that technically says we can pinpoint the attack region if the graphical mutual incoherence is less than 1 for all those boundary lines. So technically, if we have a network for which this graphical mutual incoherence or AI notion is satisfied, we can solve the problem. And we tested it on real data. We considered the data for Texas. The nodes are shown in green, and some of them in red. What we did was the following. We manipulated the data for a utility in Houston. We showed it in red. So that's what an attacker would do. And we said, let's use an algorithm that the power operator used to do a state estimation. All the recovered voltages were wrong. That's the middle picture. And that's exactly what an attacker wants to accomplish. But using this idea, we were able to show that this graphical mutual incoherence is satisfied for that network. We can pinpoint the region precisely. So that's where we have an opportunity to use AI to solve a real-world problem, without assumption and make it work. And we took this to the next level, and we said this graphical mutual incoherence is important. Let's see how it works on the US grid with about 85,000 nodes. So graphical mutual incoherence is a number between 0 and infinity. If it's between 0 and 1, that means it's good. That's how our theorem works. So we said, let's look at the lines and see what lines have graphical mutual incoherence less than 1. We showed them in green. And if they violate the assumption, we showed them in red. It turns out that 60% of the lines in the US grid would satisfy graphical mutual incoherence. 60% is a good number, but it's not a perfect number. So that really tells us, this visualization tells us what part of the network are vulnerable for propagating cyber attack and misinformation, and how we can expand it or we can fortify the network to harden these things against cyber attacks. So that's what we've been working on. And let me just skip these points for the interest of time. Just skip the last topic. To summarize, there are a lot of opportunities to do learning using AI and optimization. It's inspired by these gigantic events like Campfire in California, that is a top 5 fire in the world, and also by the need in the future that we want to have a safe data-driven operation for smart grids. And there are 2 problems that are important in this research. One is anomaly detection, the other one is cyberattack. Anomaly detection can be modeled as robust matrix sensing and machine learning. And what we showed was that if the number of bad measurements is on the order of a square root of the number of good measurements, using some optimization and ML algorithm, we can detect anomalies in the system, hopefully avoid events like Campfire. For cyberattack, we introduced the notion of graphical mutual incoherence. And we did testing on the data for Texas. We were able to show that that idea really worked on real data. We were able to pinpoint the attack region. And we realized that 60% of the line in the US grid satisfy the condition, but there are a lot of holes in the network, and that's how an attacker could take advantage of the system. We have to fortify this. And I skipped the last line that says, what's the role of amount of data? That's another thing that we studied based on the notion of ML. So I stop here. Thanks for your attention.
Are there any questions? We can take a few. Just wait till the mic.
Thank you. I'm a PhD student from CMU ECU department, and I have a couple of questions about your method. First is when you do state estimation, as shown in your model, it's a quadratic function. So is it a quadratic approximation of the system, since the original state estimation problem is not quadratic? Yeah, this is my first question.
OK, so let me answer this question, and then we can get to the next one. So yeah, I was a little quick over that one. So there are 2 ways to look at how to model the connection between the state and the measurement. So if you look at the state as the voltages in the rectangular coordinates, then it's going to be quadratic. Power operators are more comfortable with modeling the state in the polar coordinate. And then we're going to have sinusoidal equation. So these 2 these 2 problems are equivalent. You can transform polar coordinate to rectangular coordinate. So rectangular coordinate is an exact formulation of the problem. So we are not doing any approximation on that.
Thank you. And the second question is about, in your model, you said you modeled 2 variables about the error. One is the small noise, and the other is more related to the anomalies. How can your algorithm separate these 2 types of variables, since they are both correspond to mismatch, right?
Yes, that's very good. I have to go. It takes time to go back. So that's a very good point, because when we have a small mismatch or error in the equation, we have to see if should we treat this as a small noise or an event that could be a cyber attack. So there are 2 results that we can get. If we assume that W is 0, that is noise, just assume that everything is 0 or non-zero as a result of a fault, we can do all these calculations. Or if we have noise, all these upper bound that we get depends on the intensity of noise. So technically, there is a threshold, and we would say if the value is less than that threshold, we regard attack as regular noise, otherwise it's a meaningful attack. But that's a subtle point that how can we distinguish a regular noise, a random noise from cyber attack? Yes.
Okay, thank you. That's impressive. And my last question is about the metric you designed for transmission lines, the GMI.
Yes.
Could you explain more on it? And it's shown the result is very amazing. So
graphical mutual incoherence is that if the data for a part of the network is impacted, so you can look at the data for a network as some sort of a matrix, some sort of VADAS, like incidence matrix. When a part of the network is affected, that means a sub-matrix of a big matrix is affected. How would that sub-matrix affect the rest of the matrix if you perform operations? For example, if you take the inverse of a matrix. So that's an impact of misinformation on a part of the network on the rest of the network. So that, and how strong that connection is. So that's where we have graphical mutual incoherence that is related to mutual incoherence in component sensing, where there is no network technically. It's just random matrices.
We'll have one more question. Detlef, you had a question?
No, that already answered the question,
Right,
because you were flashing a lot of slides and the RIP property, and I was asking, somewhere under the hood, you must assume sparsity and use compressive sensing.
Yeah, technically we don't. Yeah, that's a good thing. So this idea of graphical mutual incoherence works on every graph. So the graph could be a complete graph that is dense, or it could be a sparse. But it turns out that with a sparse, if the graph is somehow sparse, probably the likelihood of satisfaction of this condition would be higher. So that would show up at the second stage. But for the US grad, it's 60%. And we have some sparsity there.
Okay, thanks. Let's thank the speaker. And he'll be available for private conversations at lunchtime. So if you need more details, you can always